All right, it seems like every time we come up with some sort of theory of bonding, there's something wrong with it, and we have to come up with a better theory to explain things. And molecular orbital theory is trying to explain a phenomenon that we see for oxygen gas, or even more specifically, liquid oxygen. We have some videos in Canvas where we can see that liquid oxygen is magnetic. It's attracted to a magnetic field, which means that oxygen should be paramagnetic. And if there are no unpaired electrons, the compound would not be attracted to a magnetic field, it would be repelled. So we have a video on Canvas where some liquid oxygen and liquid nitrogen are poured through a magnet, and we can see that the oxygen is attracted to the magnetic field while the nitrogen is not. And this is pretty surprising because the Lewis structure of oxygen does not show unpaired electrons. So here we have a comparison between the valence bond theory that we started the chapter with and this molecular orbital theory that is ending the chapter. The valence bond theory, we think of the bonds as just belonging to the two atoms that are linked by that bond, whereas molecular orbital theory just pictures the electrons as belonging to the entire molecule, and they can be shared by anywhere that is needed. We've been looking at overlap of the different orbitals. So either hybridized orbitals or some leftover p orbitals is what we were just looking at. The molecular orbital theory combines all the atomic orbitals and forms molecular orbitals. And our valence bond theory, we were forming different bonds. We were calling them sigma or pi. For molecular orbital theory, it's going to have some bonding and non-bonding interactions. So we'll show you that in a moment. And the valence bond theory was meant to agree with the shape. So that is really what the focus is for the valence bond theories. Whereas the molecular orbital theory is going to focus on the electrons in the molecules. We're going to be talking a little bit about bond order for molecules based on how many electrons go into bonding orbitals and how many go into anti-bonding orbitals. So here is a little practice at drawing what these orbitals would look like. What does the bonding sigma orbital and the anti-bonding sigma orbital look like? We're going to start out with two separate s orbitals, and when they combine we can make two orbitals in the set. We're going to have one orbital where we have a lot of overlap. So these electrons are being shared between the two nuclei. And here are the two nuclei with most of their electron density away from the other. So this is an anti-bonding. This is a sigma anti-bonding orbital, and this is a sigma bonding orbital. So this is what it looks like for s orbitals. Here we're going to take some px, which is p that goes along the x-axis. So here's one of the p's. Here's the other one. So when these two combine, we can have most of the electron density kind of in between the two nuclei. A little bit of another lobe on the outside. So here we have our sigma bonding orbital. In the anti-bonding orbital, more of the electron density is pushed away from the other nucleus, so it's not bonding with it. So we call this sigma star, and it's an anti-bonding orbital. Let's see if we can fit the other one on the page too. So here are some y, the py orbitals. So they are the ones that have the lobes going along the y-axis instead of the x-axis. So if we take two atoms that are going to overlap those orbitals, we get a bonding orbital where the overlap is pretty extensive, but it is above and below the line that goes between the nuclei. So that's what makes it a pi bonding. And then the anti-bonding, here are our two nuclei. So these p orbitals, instead of coming together and overlapping, they're sort of getting pushed away from each other. So this would be a pi anti-bonding molecular orbital. This is the one where it is in the y-axis. It's a little bit easier to show on the paper. This is the one where the p orbitals are on the other axis. They're on the z-axis coming in and out of the paper. So here we have y, x, and z-axis. So we have to have these lobes coming in and out of the paper. I'll do my best here. So here they are, they're trying to go in and out of the paper. The pi bonding orbital has this overlap both in front of the screen and behind the screen. There's still that node between the two nuclei. And if instead of overlapping, these lobes sort of pushed away from each other, that would be the pi anti-bonding. We still have a node in between the two nuclei, so it is still pi. So that would be the anti-bonding orbital. If you picture these two lobes kind of coming out of the screen close to you and these two going back into the screen. So how do these molecular orbitals work and what do they tell us? We can make what's called a molecular orbital diagram. And what that is bringing together the atomic orbitals. Here we're going to have some elements that are in the second period, and this is their valence electrons in the 2s and 2p orbitals. We'll bring those orbitals together to make the same number of molecular orbitals. So we're bringing together 4 and 4 to make 1, 2, 3, 4, 5, 6, 7, 8 molecular orbitals. And then when we populate these molecular orbitals with the electrons, the valence electrons that are in the molecule, we can tell whether we have any unpaired electrons. So this explains compounds that are paramagnetic versus diamagnetic. And we can also calculate what's called the bond order, which tells you how likely it is for a compound to form and how strong the bond between the atoms is likely to be. However, these molecular orbital diagrams get very complicated very quickly, so we are just going to be looking at diatomic molecules where we have two of the same element coming together to make a small diatomic molecule. Like, for example, 2 beryllium atoms making beryllium-2. Beryllium has 4 electrons altogether, and so it has 2 in the 1s orbital and 2 in the 2s orbital. We're going to go ahead and focus on the valence electrons that are in the 2s orbital, but the 1s electrons are actually doing the same thing. It looks almost the same. So we'll put 2 over here and 2 over here. So the thing that these 2s electrons are doing in the molecular orbital is pretty much the same as what the 1s electrons are doing. So when we bring together these s atomic orbitals, we create a sigma bonding orbital and a sigma anti-bonding orbital, like we looked at before in those pictures. When we bring together 2p and 2p orbitals, we create a sigma bonding and a sigma anti-bonding, and we also create 2 pi bonding and 2 pi anti-bonding. Again, in the previous diagrams that we just did, we tried to look at what these orbitals would look like. I won't go over all of them, but I'll just go ahead and look at the S and the S. Remember, when they came together, they made a bonding orbital and an anti-bonding orbital. And both of these were sigma because the overlap or the lack of overlap happened in between the two nuclei. So that's why these are sigma type of orbitals. All right, we'll bring these 4 valence electrons together, and we will put 2 in the lower energy first, and then we have 2 more. They go in the higher energy. So 2 of these electrons end up in a sigma bonding orbital, and the other 2 end up in a sigma anti-bonding orbital. The bond order can be calculated by putting the number of bonding electrons and then subtracting the number of anti-bonding electrons and taking that result and dividing it by 2. So in this case, we have 2 bonding electrons. We're going to subtract the 2 anti-bonding electrons and then divide the whole thing by 2, and that would come out to be 0. So these bonding electrons are sort of canceled out by these anti-bonding electrons. So if we have a bond order of 0, then that means that a stable bond cannot form. So beryllium-2 is not a realistic compound. So beryllium does not exist as a diatomic molecule because beryllium-2 does not form a stable bond. So the 1s electrons do pretty much the same thing. We have 2 in each of these atomic orbitals. When they come together, 2 of the electrons go into an anti-bonding and 2 go into a bonding orbital. So any type of orbital that is full, when you bring them together, they form an even number of bonding and anti-bonding orbitals, and so they cancel each other out by being 0. And that's why it is okay to ignore the 1s2 electrons like we're going to do, and we will mostly be focusing on the electrons that are in the 2s and the 2p orbitals, the valence electrons, when we work with these atoms in the second period of the periodic table. There are 8 elements in the second period of the periodic table that we're going to be looking at, and 5 of those 8 experience what is called sp mixing. And this mixing causes a slightly different order in the energy level of the sigma and pi bonding orbitals that are made from the 2p orbitals. So beryllium is one of these elements. The order of molecular orbitals that we just looked at is the order that has sp mixing as part of it. So I have drawn the same set of molecular orbitals that we saw up above for beryllium with sp mixing. The sp mixing affects this set of orbitals here, the pi bonding and the sigma bonding that come from the 2p orbitals, not the ones that come from the 2s. And in the other 3 elements of the second period, oxygen, fluorine, and neon, these 2 are reversed. The sigma bonding is lower in energy than the pi bonding. But for the first 5, lithium, beryllium, boron, carbon, and nitrogen, the sigma bonding is higher in energy than the pi bonding. So we draw the molecular orbital diagram like this. Here is a diagram from your textbook showing the molecular orbital diagrams for these elements in the second period of the periodic table. So see, this is where the sigma bonding and the pi bonding switch places. The first 5 elements, lithium, beryllium, boron, carbon, and nitrogen, have the sigma bonding as higher in energy than the pi bonding. Then oxygen, fluorine, and neon have that sigma bonding as lower in energy than the pi bonding orbitals. So let's bring 2 nitrogen atoms together and figure out the bond order, and also figure out whether nitrogen is paramagnetic or diamagnetic. We're going to be looking for unpaired electrons in the molecule. So these 4 s electrons come together and form 2 sigma and 2 sigma bonding and 2 sigma anti-bonding. Then we have 6 more electrons that are in the p orbitals, so we'll bring them together and put them in here. 1, 2. Remember, whenever you have 2 orbitals that are the same energy, you go ahead and put 1 electron in each of them before you go back and double up. That's what we did in these atomic orbitals. That's what we've been doing in the electron diagrams, and we're going to do this in the molecular orbital diagram as well. So 1 and then 2, and then 3, and then 4, and then 5, and then 6. So all of these electrons end up paired up. That means it is diamagnetic. It will not be attracted to a magnet. Also, let's look at the bond order. I'm going to mark off the bonding electrons in green here and the anti-bonding in pink. So our bond order, we have 8 bonding electrons minus 2 anti-bonding electrons. Then we divide that by 2. We get 6 over 2, which is 3. So this reflects the fact that we usually draw nitrogen as having a triple bond, and then the diamagnetic is supportive of the videos that are posted on Canvas showing that the liquid nitrogen is not attracted to a magnet, but the oxygen is. All right, so let's take a look at the oxygen and see why would it be paramagnetic, and also see what the bond order is. So let's write down a reminder. The question doesn't mention the bond order, but we'll figure out the bond order as well. All right, this time instead of drawing the 2s and the 2p on the side, I've just drawn the molecular orbitals in the middle. These two have switched places. Instead of the sigma bonding being higher in energy, it is lower in energy. And instead of drawing the electrons of each oxygen in their atomic orbitals, I will just keep in mind that we have 12 valence electrons that we need to populate the molecular orbitals with. So we'll go ahead and start putting them in 2, and then 4, and then 6, and then 7, 8, 9, 10, and then 11 and 12. So when we do this, we end up with unpaired electrons in this anti-bonding, the pi anti-bonding orbitals, which means that it would be paramagnetic. And then I'll mark off the bonding electrons and the anti-bonding electrons to get the bond order. So we have 8 bonding electrons and 4 anti-bonding electrons. We divide that by 2, which gives us 4 over 2, or 2. So that matches what we know for oxygen, that it has a double bond, or the Lewis structure is drawn with a double bond. It does form. The bond order is not 0. Then we have one more question here about the charge that an oxygen molecule would have to have in order to become diamagnetic. So let's look at these unpaired electrons. If these were both gone, so if one of them were gone, we would still have an unpaired electron. But if both of them were gone, we would have only paired electrons. So to be diamagnetic, we would have to have 2 electrons gone, and that would give it a +2 charge. So if these 2 electrons were gone, and we have oxygen molecule with a +2 charge, that would be diamagnetic. Another possibility is if we added 2 electrons. If we only add 1 electron, we will still have 1 unpaired. But if we added 2 electrons, then that would also be a diamagnetic molecule. So if we had a -2 charge, that would also be diamagnetic. But a +1 charge or a -1 charge would still be paramagnetic. So let's go ahead and draw molecular orbital diagrams for a carbon diatomic molecule, a beryllium diatomic cation, and an oxygen diatomic anion with just a -1 charge. I'm going to do the same thing I did on the previous page and only draw the molecular orbitals, not the atomic ones, so we don't have to use as much room. For beryllium and carbon, I'm going to draw them in the order that has this sp mixing, with the sigma bonding higher in energy than the pi bonding. And for the oxygen, I'm going to draw the molecular orbitals that have the sigma lower in energy than the pi bonding of the p up here. So these are the ones that change places in their energy level when you have sp mixing. Now I will count the number of electrons that have to go into these molecular orbitals. We'll count the valence electrons. Carbons each have 4 valence, so altogether a carbon-2 molecule that is not an ion would have 8. The beryllium each have 2, so it would be 4 for the molecule like we did before. This one is missing an electron because it's a cation. And oxygen would have 12, but this one has an additional valence electrons because it's an anion. So let's go ahead and populate these molecular orbitals. So here are the 8 valence electrons here, and here we have 13. So to predict the bond order, I will go ahead and highlight which electrons are bonding and which ones are anti-bonding. And then I can calculate the bond order. We have 6 bonding electrons, 2 anti-bonding electrons. We'll put that over 2. So that is 4 over 2, which is 2. So carbon would have a bond order of 2. Beryllium's bond order, I'll put up here. We have 2 bonding electrons, 1 anti-bonding electron, and that goes over 2, which is 1/2. We can also write that 0.5. So beryllium cation here is a 0.5 bond order. For oxygen, we have 8 bonding electrons, 5 anti-bonding electrons. So that makes 3 over 2, which can also be written 1.5. It's 1.5. So looking at these 3 bond orders, we can see that carbon has the strongest bond. It has the highest number for its bond order. So which of these would have the strongest bond? The answer is the C2 molecule. So in the same way that an atomic orbital diagram, which looks like this, can be abbreviated as just the electron configuration, just naming the orbital and putting how many electrons are in it as a superscript, we can also do this with the molecular orbitals. We can name these lines. We have this molecular orbital diagram from before, and I did not really specify. I was just writing sigma and sigma bonding and sigma anti-bonding. These are the ones that come from the 2s, and so these can be named as the sigma with 2s as the subscript here to show that this is the sigma that comes from 2s, and this is the sigma anti-bonding that comes from 2s. So you can put these subscripts here, and that's what these 2 orbitals are. Then comes another sigma. These ones come from the 2p. The sigma comes from the 2p that are along the x-axis, because these are the ones that face each other and make a sigma bond. So these are the 2px. The sigma bonding and the sigma anti-bonding are like that. So we have 2px as the subscripts for the sigma bonding and anti-bonding. The other pi bonding and pi anti-bonding come from the py, the ones that are next to each other up and down in the y-axis. So this is a pi bonding orbital, and also the anti-bonding orbital. And then the Z coming in and out of the screen, which is hard to draw, also creates a pi bonding and a pi anti-bonding. We looked at that like a couple pages ago. So we can name these pi bonding and pi anti-bonding as coming from the 2p Y and Z. So that's what those subscripts mean. So if we wanted to draw an electron configuration rather than an orbital diagram for these molecular orbitals, we could write it like this. So if we wanted to, we could draw a molecular orbital diagram to match what this electron configuration is, but we could also just mark off which ones are bonding and which ones are anti-bonding. So we could figure out the bond order pretty easily. We have 2, 4, 8 bonding electrons, and we have 2, 4, 7 anti-bonding electrons, and we put that over 2, which would be 1/2 or 0.5. So this molecule would have a bonding order of 0.5. Figuring out whether this would be paramagnetic or diamagnetic is a little bit trickier. These ones are full. The sigmas, these sigmas are full, and these pi's are full, so we know that they have no unpaired electrons. This one, the last orbital, has just 1 in it, so this would be an unpaired electron, so this would be paramagnetic. I would just say to watch out if you have pi bonding or pi anti-bonding orbitals that are not full. Remember that there are 2 of those, so like oxygen. So I just want to point out that if we did this electron configuration for the molecular orbitals of the oxygen molecule with its 12 valence electrons, we would see 2 in the sigma bonding, then 2 in the sigma antibonding, 2 in this sigma bonding, 4 in this pi bonding, and 2 in this pi anti-bonding. So even though it looks like there might not be any unpaired electrons, remember that for these pi, there are 2 of them. So here's this pi anti-bonding. If there's only 2 electrons in here and not 4, so if it's not full, the pi anti-bonding or either of the pi orbitals, if they are not full, 2 electrons are still going to be unpaired. So if the sigma has 1, it's going to be unpaired and paramagnetic. Once it's full, it's paired up. The pi orbitals, if they have 1 or 2 or 3 electrons in it, all of those scenarios are having unpaired electrons. The only time that it's completely paired up is when it's full with 4. So having 1 or 2 or 3 electrons in the pi orbital would have unpaired electrons. So these would be unpaired, making oxygen paramagnetic. So if you see this abbreviated electron configuration for these molecular orbitals, I think it's pretty easy to decide the bond order. To decide whether something is paramagnetic or diamagnetic, just be careful of the pi orbitals, that they have to be completely full to have no unpaired electrons in them.